Okay. Este curso es microeconomía gerencial. Ustedes que vinieron pues, llegaron bien a las 7. ¿Pueden llegar a las 6:30? No problema. ¿Cuándo llegas hoy? Es que no puedo escribir aquí. ¿Cuándo llega el jtorres.uprrt.edu? Esa es mi página. Y tiene toda mi información. Mi oficina, que estaba en el 5º piso. La extensión de teléfono, mi email. Mi hora de oficina, van a ser lunes a las 6, miércoles 4:30, 12:30 4, o por cita. Generalmente el día antes de esta clase puede ser cita conmigo. Los otros miércoles cojo mi mes, no puedo, pero antes de esta clase. Entonces, tengo todos los cursos que enseño este semestre. El link que ustedes es el segundo. Ya escribieron todo lo que necesitan. Pues si tú vas al link, es el portal. Tiene toda la información, los prerequisitos, objetivos, definiciones, básicamente el horario del curso, los cursos que vamos a hacer y el tiempo que la vamos a cubrir. Oops, sorry, that's not right. It'll be around then, pero eso es algo que no cambié del semestre pasado. Bueno, del año pasado. Cuando son los dos exámenes parciales. Antes di la opción de un examen parcial o dos. Nunca votaron por uno, pues ya ni tanto. El texto, Nicholson Insider, 2011. Yo creo que ya tienen el 10º, 12. Ok, es otra cosa. El curso va a estar enseñado en inglés. Yo hablo español, pero cuando comienzo a enseñar en inglés me tranco porque pienso en inglés. I translate in my head, and once I start teaching, I have too many things going on. I lock up. So, okay. Esto es negociable, 25-25 por los dos exámenes parciales, 15% por las tareas. Después del huracán, yo no estaba dando tareas, la estaba dejando opcional. Yo creo que lo voy a hacer una vez más. Eso quiere decir que esos 15% te las doy gratis. Ley 51 de la universidad y otros libros y referencias. Y aquí tengo las lecturas y unas asignaciones y unas pruebas de examen. Generalmente lo que yo hago es yo voy poniendo como curso. Otra vez después del huracán voy a dejar todo eso. A ver. Ok, está el texto. Ok, hay preguntas. Tenemos 8, yo creo que tenemos 10 matriculados. Hay una señora que no puede venir los sábados por trabajo. Y tenía otra que no, caí. ¿Perdón? Sí. Ok. Ok. ¿Perdón? Tengo 3. Yo entendí que tenía 2. ¿Perdón? Oh. ¿Tú eres el trabajo entonces? Sí. Ok. Habla conmigo después del examen, del curso. Ok. Ok. Entonces, este semestre es uno de vamos a decir prueba. Este semestre muy bueno a los prerequisites. Y por eso yo sé que algunos de ustedes no tienen la matemática que generalmente uso en este curso. Pues, right now, the material is the same. I'm going to try to cover it as best I can. What I usually do this first day, it's basically, I hope usually, it's a review. I'll talk a little about microeconomics and managerial macroeconomics, and then I go in and I review some math. Today I'll do less of that because I don't think it's going to be reviewed for most people. But it is very important that we try to catch up on the math. Math is a tool. And for higher level economics, it's a necessary tool. And without the tool, it becomes very hard to do. It basically becomes an undergraduate without the math. So we'll do our best and we'll muddle through. And like I said, you guys have a lot of math this semester that you have to try. Okay. Y tienen el curso de Javier, ¿no? Ok. ¿Vamos con eso? Hay preguntas antes que generalmente, el curso, las lecturas van a durar 2 horas. Esta noche va a ser un poquito más porque tengo la matemática. So most likely we should be out of here by 9. Unless we're trying to either make up or get ahead. And we might do that if, I don't know, if it looks like there's going to be a strike or something like that. I can't give this course as a hybrid course, even though it's listed as it, because I'm supposedly not qualified. So it's going to get, the most I can give is 25%. I can broadcast the course most days, or most of the times I'm here, but there's always, every time I try to broadcast courses, there's always been a course or two where I have problems. Either I make a mistake, I forget to hit a button, or whatever it is, or Wi-Fi is just out, or something else is wrong. But I will do it so that if one day you can't make it, send me an email, and basically what you have to do is log into Hangouts. And if you have a university account, that upr.edu, if you have that account, you have Hangouts. It's part of your account with the university, because that accounts to Google, and Google has Hangouts and YouTube. Also, hopefully at the end of the night, this lecture, or what you see up here, will be on YouTube. And hopefully it'll look better than this. No. Sorry, Eddie. Which is that better or that better? That one? Okay. Okay. And either way, it's not very good. Okay, well, let's start. The first thing I want to talk about is just economics in general. The first thing I want to define is the difference between what we call positive economics and normative economics. Positive economics is only concerned with facts, right? What is? What's happening? It's either true or it's false, right or it's wrong. Normative economics, on the other hand, encourage value judgments. What should be? Now, in general, we try to practice positive economics as much as we can, and then once we get to a point, then we can start talking about what should be. Methodology. I'm hoping someday we'll get that moved up. I thought they were going to take care of it, but I haven't. It just has to be like that in a couple inches. Anyway, methodology is simply the way in which we examine economic questions, and that's going to determine, right, whether we're practicing positive or normative economics. The truth is, it's hard to be fair because we're human. We have our prejudices, we have our bias, and we have our beliefs. So we're going to steer towards what we usually think should be the correct answer. Which brings me to a methodology called modernist methodology. Now, this thing is old. This thing is older than I am. I'm 53 years old. This thing was developed in 50. So I don't know if modernist is the correct term for it anymore, but it's basically what you should do in any type of academic or scientific endeavor, right? The first thing we want to do is prediction or control is the key. We want to know exactly what's going on. If we know all the inputs, we should be able to figure out what that is. Only observable implications of a theory matter. We'll talk about exactly what a theory entails a little bit. But that, if you can't observe what's going on, you can't say whether a theory is right or wrong. So therefore, unobservable implications simply doesn't matter. Observability entails objective, reproducible experiments. Now, for us in social sciences and business science, we don't get really to experiment very much. Basically, what we do is we collect data and we use statistical techniques to test the data to prove our hypotheses. But even there, if we have different data sets, say from different countries, different whatever. If we do the same thing and our theory is correct, we should get the same results with different data and different methodologies or different statistical techniques. If predictions of a theory are shown to be false, the theory is false. But the opposite isn't true according to the modernist methodology. In other words, what that means is that if oops, I went too fast. That's okay. What that means is just because the evidence or the experiment or whatever you did supports your theory, it doesn't mean that it's true. What that means is there's evidence for the theory, nothing more under modernist methodology, because there might be something else going on. And even if you prove a theory false, in general, under modernist methodology, the theory is false. If the result is false, the theory is false. But in reality, there might be something else going on. It may be that we just don't have the proper tools to test what we want to test. Okay, objectivity is a key. Again, if we're observing positive economics, and some subjective observations are discouraged. You need to be as objective as possible. And again, just like observability, if you can't express it in numbers, which gains no satisfaction, we need to measure. If you can't measure it, well, then the results really would be hard to say that the theory is right or wrong, or that we have evidence for or against a theory. And finally, subjective thought may be used to manufacture a theory, but it can't be used to just You have to actually go out and prove it. Of course, because we're human, right? Nobody follows this methodology completely. The best we can do is do the best we can. Try to be objective. Say right here, economics basically wouldn't be a science if it was followed perfectly. And again, for better or worse, falsification. This is what we were talking about with theories, right? With theory, prediction are proven false, with theory must be false under modern methodology. But it might be that the theory is proven false because it's impossible to adequately test, right? The prediction. This is because most hypotheses, at least in economics, can't be isolated. Again, where you don't have the luxury that the hard sciences do, you can't do experiments. We can't let people on a desert island and increase certain resources, decrease certain resources, and see what's going on and see what happens. They've done it with mice, kind of it, and you get some validity for economic theory and microeconomic theory, but it's still not satisfactory. Okay. There are some things that the majority of economists agree with. For instance, over 90% of economists believe that tariff and input quotas reduce the welfare of both the nations involved. And rent ceiling reduce the quality and quantity of housing available. So if you have rent control somewhere, after a time, the amount of apartments available and the quality of those apartments starts to decrease. Right? Pretty much, like I said, the vast majority of economists believe things like that, or certain things. But it doesn't tell us, it doesn't tell us by how much. For instance, how much is welfare reduced if we have tariffs? It also doesn't tell us that if we're actually talking about two big nations, right, what subgroups in those two nations are affected. Might it be that some subgroups benefit from the tariffs and some don't? Okay. Other widely held predictions of economics cannot be adequately tested, and neither can these. Why? Because we can't control. There's 100 things going on, and we can't control all of them. The best we can do statistically is try to control it. But our statistical techniques just aren't adequate enough to control it perfectly. What we really need, right, is to be able to control the actual variables, like you do in a laboratory experiment. Okay. Questionnaires are pretty popular in social science and in some business science disciplines. For those of you in international business, if you concentrate on the marketing aspect, in marketing, they do tons of surveys. Economists tend to frown on surveys and look at them as unscientific for two reasons. One, people may not be truthful in surveys. And two, they may intend to be truthful, but really don't know how to answer the question. And here's the famous example. This is Milton Friedman. He won the Nobel Prize like back in the 60s. He's still alive. He compares it to a physicist surveying a billiard player, a pool player. Basically, the surveys, right, and the answers the pool player is going to give really isn't going to be any value to the scientist. All it's going to do is confuse, and it's not going to help him with the physics. Again, it's the same thing with the business person or consumer. He might be the best business person in the world, right? But he may not understand the economics of what he's doing. Therefore, a questionnaire may not help you understand what's going on. Go ahead. Es posible. Pero la pregunta es, ¿verdad? El jugador no entiende la física. He doesn't understand the physics of the game. He plays well, We understand, and it might be that you can, after knowing or having a good theory, and actually knowing the physics of it, you can produce a questionnaire, excuse me, a questionnaire that will help you understand the physics by the questionnaire, but that's after you already understand the physics. But see, that's the thing, if you have a theory and you ask those questions to support the theory, thinking the theory is right, that's exactly what you're going to get. You're going to get a confirmation of the theory, even though the theory may not be right. And that's basically the problems that economists have with questionnaire. Like I said, this is a basic example, but I understand your point. Once you understand the physics, if you actually understand the physics, then you can probably come up with a questionnaire that will confirm what you know. But if you don't know with certainty, like we don't know with certainty exactly what the theory should be or what's actually going on, like right, then your questions are going to either confirm your theory if you ask it in the right way. And that's not what we're supposed to be doing. We're supposed to be objective. And objective questions will tend to confuse physics. Okay. So now I'm going to define theory. Every year I have students ask me, is the test going to be theoretical? And I never know how to answer that question. Theory for us is a set of explanations or projections about various objects in the real world. Right? A model, on the other hand, is simply a logical system. The model can become a theory when assumptions relating to theoretical constructs to a real world are added. So basically for us, a theory or a model can be thought of as a story or a metaphor. Right? And we hope that theory explains the real world. Okay, this will be lecture 1 on the links. Okay, for those of you old enough or live in the States, there used to be a commercial for VA veterans. And I sold this part of the lecture from an old professor of mine, so I'll tell you back in that commercial, the guy would go to the fridge and pick out a card or something. He noticed the VA vegetable juice, and he'd clunk himself on the head and say, I could have had a VA. That was a commercial, right? That's an example of opportunity cost. Anytime you're doing something or spending resources on one thing, you're foregoing being able to do something else or spending resources on something. So that is opportunity cost, right? So the underlying idea is derived from the concept that when an economic decision is made, there's a goal, and that the decision maker, or we're going to call agents, he wants to achieve that goal. So all the choices are made with some limitations or constraints to acquire one thing, something else must be given up. Right? Those are opportunity costs. Right? For example, when I spend money on one purchase, I forgo the satisfaction I would have received from spending that same money on something else. Right? And here's an example. Right? Suppose I was working and I was making 12,000 a month. Now, from a accounting point of view, right, I'm making a profit. I'm doing really well in my business. But, right, if I could have worked for somebody else and make more money, right, then my opportunity costs in that case are positive or greater than half. And what that means is, even though I'm making what we call a business profit, I'm actually making an economic loss. My economic profit in this case is negative if I was making more of this. Now, if I could just make $12,000 working for somebody else, then my economic profit would be zero. Now, when we get into perfect competition later on after the first midterm, right, we're going to learn that under perfect competition, theoretically, everybody makes zero economic profit. Business. That is because they're just making as much as they could in the next best alternative. Okay. Rationality, goals, constraints, and behavior. Right? When we talk about rationality in this class, we might not be thinking of what you usually think as a rational person. Right? When we talk about rationality, the first thing we assume is the agent has a goal. Right? As long as his behavior is consistent with achieving that goal, we say he's rational. Now, it might be a drug user, and we wouldn't think of a drug user as rational, so at least somebody who's addicted, we wouldn't think of them as rational, but for our purposes, he would be rational, right? Because all we care about is that he's behaving in a way to achieve his goal. Right? So if you're, let's say, a business, and you run the business, you're the manager, that agent goal might be to maximize profit. It might be something else. It might be to maximize revenue, maximize market share, minimize costs. For the most part, we're going to assume for businesses to maximize profit for our purposes. For a consumer, we're going to assume generally that his goal is to maximize the satisfaction and social. And that satisfaction we're going to call utility. Okay. So how do I spend my money? Perhaps I have some way of comparing different baskets of goods if I'm a consumer, right? In other words, I could have bought this basket of goods, this basket of goods, or this basket of goods. Out of all those baskets of goods that I could have bought, which one do I prefer, right? And then we're also going to talk, right, about constraints. Right? For a business, the constraints are usually technical. How much I can produce, and then my input, right? How much input can I get? Those are usually constraints for business. For a consumer, our constraints are usually our budget. We call that a budget constraint, right? We all want to have that big yacht, right? Get paid to drive sports cars or Rolls Royce or luxury cars. We want the nice cars, the yachts, the big houses, etc. But we usually can't get those things because we're constrained. We simply don't make enough money. Okay. Comparative statics. Most of the things we're going to do in this class involve comparative statics. What comparative statics is simply we take a picture or we take the situation at one point in time, we change something, and then we compare that to the situation or picture at another point. For example, let's say we have a sales tax. How would it alter the environment that people operate under, and how would it alter their behavior? Right? Given the information, given economic theory, we can make projections. Right? Later on, we're going to figure out what something known as elasticity. Right? When things are inelastic, the demand is strong, and we usually don't switch out of them when price, or we don't switch out of them as quickly when prices rise. Right? So if we know the elasticity of something, we can tell what the demand is going to be for it after, say, something like a sales tax occurs. Okay. Economics in the real world. We're not modeling the real world in this class. We're trying to come up with simple models. When you look at them, when you look at the mapping, I think they're simple, but they're simple compared to the complexity of the real world. Is this getting darker? Or is it just me? Okay. You got to be joking. It's kind of a bluish tint, but it's better. Okay, so we're not modeling the real world in this class. What we are attempting to do is analyze theories that we hope will give us enough information that we can make predictions about the world. We want to use to get our predictions, to get correct predictions, the simplest models possible. Now, what that means is our models may not always be correct. And to get those models, we have to make a ton of assumptions. And those assumptions may not always be realistic. But if we can predict behavior, that's what we're looking for. And sometimes we might want to change those assumptions, right? If we're analyzing something a little different. For instance, one thing that we don't do is I assume that if I like something, I like it no matter what it's fixed. And I assume prices are fixed, and I assume tastes don't change from moment to moment. All those things are bad assumptions. In the real world, all those things happen. Now, the example I have here, would I like diamonds just as much even if they were cheap? I really don't like diamonds, so yeah. But there are a lot of people, females mainly, that like diamonds. Now, the question is, would they like them as much, right? If they were cheap. If you could buy a 1 carat diamond for $5, would you like it? Would you wear it? Or does the status of it being expensive, right, get it or make it more attractive? Now, if I try to put that in my simple economic model of the consumer, it would explode. It's just difficult to do. Because the price rises, then I start liking it more. We probably end up getting upward sloping demand curves. And we see that later on. We talk about them. You'll see that blows our competitive status. We're not really modeling the real world. We're making assumptions that aren't always realistic, but in most cases they work. Comparative status can tell us many predictions. For instance, I have changed this a few times. Aid to dependent children, basically the layman's term is welfare. And this was the way this was called back in the 90s. We changed it a few times. Every time they change it, I try to change it. I don't know, state up and change it. It's basically in the States, they give people from state to state money, right? When they're unable to find a job or don't have the relative income. Now the question is, right? Does that money discourage people from working? And most economists will say yes, it's discouraging. The problem is, even though it's a disincentive to work, right? You don't know how big that disincentive is. You didn't know how much rent control or how much tariffs affect work. But once we get down to figuring out the general direction of things, and we can test them, then we can go ahead and test and see what the magnitude is. Right? For instance, most economists believe or would argue that raising the minimum wage would increase, right, or decrease the job opportunities for low-income workers. But not all economic studies have shown that to be true. Okay? And why? I don't know. It might be that there's other things going on. And even though we try, and in some cases, the argument's very good that we've controlled for it, we may not be. Or our theory may just be wrong. Okay. Okay. So the bad thing about this class is I don't have room to write on the board. All the other classes are in.
Yes, I think so.
Okay, I'm going to ask to see if we can maybe switch to when we get a just so I can write on the board. Anyway, as Is anybody in here who's never had an economics class? So everybody's having, don't be shy, it's not. Everybody in here is having economics class. Okay. All right, then you've seen this diagram. This is our basic supply and demand diagram. We have price on the vertical axis, quantity on the horizontal axis. We have a downward sloping demand curve and an upward sloping supply curve. And where they meet, right, is our equilibrium price. Now, what I usually do is I draw on the board here. I don't have enough space. What would happen if price was above the equilibrium price? Let me try to draw it. I guess I could do that. Okay, so I have my basic supply and demand diagram. If price is above the equilibrium price, call it P prime, right? Then more is being supplied than is being demanded. That's called excess supply. Right? What happens then? Well, inventories start building up. Right? The company can't sell what they're making. What do? They put on a sale, lower the price. And they keep lowering the price, right, until they get to a situation where they're selling, right, at that price, all that they're making. So at that price, they're willing to sell this much, and they're selling all that they're making. What would happen if we have the price down here below? Let's call it a P-double prime, right, below the equilibrium price. Well, in this case, right, more is being demanded than is being sold. That's excess demand. When that happens, the company can't keep its inventory on the shelves. It's flying off. Well, they realize that they can sell as much as they want, right? Even if they raise the price a little. So they keep raising the price and raising the price until, right, again, they get to a point where they're selling just as much as they want to. And they have a normal, the stuff goes off the shelves quickly, but quick enough for not so quickly that they can't replenish it. Okay. So here what we have, right, is an equilibrium at P star, and equilibrium just means a state that's stable and there's no tendency to change, right? That's our equilibrium. So we have that stability where P star, it's at rest, right?
Esto es tu opinión. ¿Crees que se debería en situaciones como María viven a un precio?
Perdona,
En una situación de escasez, como ocurrió con María, ya sea con la gasolina, botella de agua, ¿crees que se debe poner un ceiling al precio, un top al precio o no?
That's normative economics. And in my opinion, there are times when that's appropriate. And that's only when you know, right, that there's not going to be enough supply to meet the demand, right? And you're going to have an incentive to increase. In those cases, rationing is justifiable for a short period of time. That was my opinion. That's my opinion. For instance, during World War II, the U.S. did that. If you wanted to buy gas, it didn't matter if you just had the money. You needed coupons that says, you know, this is how much gas the government letting you buy, and the money. So legally, even if you wanted to pay double, legally you couldn't do it. Okay. We talked about positive and normative economics, and now we're going to get into math. So, okay, here's some notation. The first one, right? Here I have capital X, right? Is a set of elements X such that f of X is at least as great as, or at least as large as, X naught. Now, for some reason, when they put the 0 up above, or this little circle up above the X, they call it naught. Mathematicians do that. I don't know why. They do it, so I do. X naught. If you have a little upside down A, that means for all. A backward G means there exists. ST for most of mathematics means such that. For our purposes, most of the time, when I write ST, it's going to mean subject to. Because we're going to have, excuse me, we're going to have an objective function, right? That thing that we want to maximize. And we're going to have a constraint. So we're going to have our objective function subject to our constraint. Right-hand side, RHS, left-hand side, LSH. LHS. Okay. I'm just going to go through this real quick. If we have two lines, that's what you've seen since first grade. It means equal to. Right? 1 plus 1 is 2. If I have 3 lines, that's an identity. That's something we're setting equal. This is identical to something else. That means if I have an identity, that's always going to be true. This is set equal to. I'm going to skip the proof for the example. Okay. And I'm going to jump straight into calculus. All of you have had a class that's supposed to have calculus in it. I know that. But I also know that a lot of times the professor don't go as fast as the syllabus says. So I'm going to assume that there's at least one of you in here that's never seen a derivative. I'm going to try to go slow, but if you took a class that has derivatives, what you usually see are these rules, right? And the first thing they do was they start taking limits and do it, and they prove the rules. I'm not going to prove the rules. I'm going to show you the rules. I'm going to give you some examples of the rules, and then we're going to move on. We're going to do this over and over, and hopefully in Javier's class you'll do it over and over. So basically, the semester is going to be very quantitative. Okay. The first one that's up there on the little metal thing is called the constant function rule. Okay. What's a derivative? A derivative tells us the rate of change. Right? Basically, one variable affects another and how fast it moves, how fast it changes. The rate of change of a function, let's say. Okay. If you have a constant, something that's constant, how much does it change? Yeah. 0, exactly. So the constant function rule is very intuitive. If you have a constant, the derivative of that constant is 0. Just so you can write it down if you're writing. Like I said, I know you guys are writing down now because you didn't know. Because people ask. Okay. Actually, yeah, it doesn't matter where I put it. It's not going to work. But now you can at least see the constant function rule, right? The change in k with respect to the change in x is 0. I have a constant. The derivative of that constant is 0. The rule that we're going to work most with in this class, and the simplest, other than the constant function rule, is known as a power function rule. So I have a derivative, right? X to the n power. When I take that derivative with respect to x, the derivative is going to equal n x n minus 1, right? A lot of times mathematicians, instead of writing out the derivative dx, where d is supposed to be the Greek letter delta, dx to the n divided by dx, right? Instead of doing that, they'll write it f prime x of n. That's the first derivative. So, right, let's say we have a function y is equal to 5x to the 4th. What I want is a change in y, dy, over dx. Now, using the power function rule, I'd like you guys to attempt, right, to solve this derivative, right, dy dx. Give it a minute. Go ahead and write it down. Do your best. So all you have to do is follow this rule. Here, n is 4, right? And that 5 just stays there. It's multiplied, right? So in that case, it just stays there, and you apply the rule. In other words, I can do this. I'm going to say 5 dy dx, right? And basically, I use 4 as n, right? So it'll be 5 times n, right? And then on the top, it's n minus 1. Okay. Did y'all write it down? Did I turn around and I missed it? Okay, so I have 5. Now n is 4, so I'm going to bring the 4 down. That's n, right? Times x, n, which is 4, minus 1. Right? Now I can rewrite this. That's 5 times 4 is 20. Times x, 4 minus 1 is 3. So it's 20x cubed. So dy dx is 20x cubed. Does that make sense to everybody? Okay, suppose I have a function y equals 3x to the 6. What would the derivative of that function be? Okay. I wanted you to write it down, so that you can see how we work on it. That's it. Hopefully you said it too fast and nobody will hear it. For some of you, this is boring. For some of you, my sense is that it's just Chinese or Greek or whatever, some foreign language. But as he said, I'm going to have 3. Now, in this case, n is 6, so I bring 6 down here. So I got 3 times 6, x, 6 minus 1. So I have dy dx 18, 3 times 6, x to the 5th. Okay, y equals 5x squared. Dy dx, in this case, n is 2. Okay. So I get 5 times 2, because we know it's 10, x, 2 minus 1, right? And that equals 10 x to the 1 power. And of course, we know that x to the 1 power is simply x. We got 10x. Let's do a real simple one. Y equals 3x. So dy dx, in this case, right, what's n? 1, perfect. So I have 3 times 1, x, 1 minus 1. So that equals 3 times 1 is simply 3. X, 1 minus 1 is 0. So I have 3x to 0. X to 0 is, so I have 3. Okay. The next thing I want to talk about is the sum difference rule. And it's very simple. It's if I have basically one equation plus or minus another equation, I take the derivative of one and I add or subtract, depending if it was added or subtracted to it, the derivative of the other. Right? So so if I have the following, what would dx dy be? Okay. In this case, I do it one at a time. I do the first one, and here n is 2. So I have 5 times 2, x 2 minus 1, and then I subtract, and here n will be 3 on the second part. So I have 3 times 3, x 3 minus 1. So this is 10. X 2 minus 1 is x to the 1, minus 3 times 3 is 9. X 3 minus 1 is 2. So it's 9x squared. 10x to the 1, or just 10x minus 9x squared. Equal the curve. So I have here y is equal to 5x plus 5x to the negative 2. So dy dx in this case. So I do the first one here, x is 1. So I have 5 times 1, I'm sorry, n is 1, times 1 minus 1 plus 5 times negative 2 times x negative 2 minus 1. So here I have 5 x to 0 plus 5 minus 2 minus 10 x negative 2 minus 1 is x to the third, and I can write that as 5x, x to 0, I'm sorry, 5, not 5x, plus, or actually we do minus 10 x to a negative 3, and I can actually rewrite this as 5 minus 10 over x to the third. Okay. Those are the rules that we use most in this class, but we have some other rules that we will use in this class. Like I said, we're playing this one by ear, so we're going to go by rule. I'm not sure exactly what to do. But in a normal class, we use all of these rules. So the first rule, or actually the fourth rule, is the product rule. Right? This is when we have two functions multiplied by each other. So let's say I have y is equal to 5x to the third times 6x to the negative 1. Now the rule, the product rule, says when I have that, what I want to do is I want to take the derivative of the first function, multiply it by the second function, then add the derivative of the second function and multiply it by the first function. So hopefully those of you who are bored, this is a little less boring, a little more challenging. Okay, so why don't we go ahead and try it? So I'm going to take the derivative of the first one and just treat this as basically a constant that's multiplied. Now, we know that the derivative of a constant itself is 0, but in this case it's multiplied, so we don't do anything to it. We don't set it equals 0, we just keep it the way it is. So here, n is 3, so I have 5 times 3, x to 3 minus 1, right, times 6x to negative 1. To that, I add the derivative of the second part, right? In this case, n is negative 1. So I have 6 times negative 1, x, negative 1 minus 1 times the first function, which is 5x to the third. So I have 15 x squared times 6 x to negative 1 plus minus 6 x to negative 2 times 5 x to the third. And of course, I could 6 times 15 is 6 times 5. But in most cases, that's enough for us, assuming I don't have to continue working to get to some other point in the problem. One more product rule. I have 5x times 3x to the fourth. Now, I know you might have noticed that I could have just simplified this and used the following. And most of the times, that's what I do. But here we're trying to show, and I don't want to make them overly complicated. Usually what this happens is when you have a log and it's hard to multiply the x's together, things of that nature. But right now I want to keep it simple, but not too simple. I want to show you the actual power. The same thing with, we're going to talk about the quotient rule. I always forget this rule. I have to look it up if I ever need it. Therefore, I usually try to simplify it so I can use the product rule. So I have dy dx. So I want to take the derivative. In this case, x is 1, so I have 5 times 1. X, 1, oops. 1 minus 1 times 3x to the fourth plus, thank you, and I didn't do it, did I? 3 times 4, n is 4, x, 4 minus 1, sorry, thank you. I'm out of it, yes. Plus, thank you, 3 times 4, x, 4 minus 1, times 5x, and thank you very much. I don't know what my head is. X to 0 times 3x to the fourth plus 12 x to the third times 5x. This is a nice. So I have 5x times 3x to the fourth plus 12x to the third times 5x. What's that?
Yes, just one.
Let's see. Oh, this was x to the 0, sorry. 5 times 3, or let me just write it as 15. Yeah, I like that. Okay. Next is the quotient rule. Right? This is where we have one function divided by another function. So suppose I have y is equal to 5x squared divided by 2x cubed. So what the quotient rule tells us is I take the derivative of the first function times the second function, and I subtract off the derivative of the second function times the first function, and I divide the whole thing by the function in the denominator squared. So I have the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator, all divided by the numerator squared. Okay. So, hopefully you guys will finish before I do. I take the derivative of the top, in this case n is 2, so I have 5 times 2, x 2 minus 1, times 2x third, to the third, minus 2 times 3, x 3 minus 1, times 5x squared, all divided by 2x to the third, quantity squared. And then I can write that as 10 times x times 2x cubed minus 6 x squared times 5x squared, all divided by 4x to the 6th. One more quotient rule, or should we move on to the chain rule? Let's do one more quotient rule. Let's see. I have 7x to the third times 4x to the fifth. X. I'm going to go ahead and start. In this case, I take the derivative of the numerator. I have 7 times 3, x to the 3 minus 1 times 4x to the 5th minus 4 times 5, x to the 5 minus 1 times 7x to the third, all divided by 4x to the 5th squared. Can you read that? So I get 21 times x squared times 4x to the 5th minus 20 x to the 4th times 7x to the 3rd, all divided by 16x to the 10th. Okay. Questions? Okay. The last rule in calculus we're going to use, I shouldn't say that because we have some others, but these are the basic rules that we're going to use when we talk about partial differentiation. They're the same thing. The concept's the same. A little different notation, a little different conceptually, but it's the same thing. And when I show you the antiderivatives, the integrals, the rules are just this definition. Okay, the chain rule. In this case, I have to assume that I have two functions. I have three variables. One function, or the second variable is a function of the third variable. And the first variable is a function of the second variable. What that means is when the third variable changes, it affects the first variable through the second variable. And I'm doing this, and it's taking forever, just because this is blocking right here. Suppose I have a function here. It's still going to go down all the way. But here's the chain rule. Suppose I have two functions. Y is a function of x, and z is a function of y. That means when x changes, it's going to affect y, and then y is going to affect z. So the way, if I want to get the derivative of how z changes when x changes, right? dz, dz dx, right? I have to do the following. First, I take the derivative of z with respect to y, and then I multiply that by the derivative of y with respect to x. Everybody done right? Now I'll let this go up, and we're going to go ahead and okay, here I have y is equal to 5x and z is equal to y cubed. So what we want is z dz dx. So first I take the derivative of z with respect to y. So I have 3y, 3 minus 1, times the derivative of y with respect to x. So I get 5 times 2, x, 2 minus 1. And so it's going to equal 3y squared times 10x to the 1, or 3y squared times 10x. That's a chain rule. It's just basically you have one variable affecting another variable indirectly in a second. Questions? One more example on chain rule, or? Suppose I have y is equal to 15x, and z is equal to y to the negative. So what I want is dz dx. So why don't I write it out? I need first dz dy times dy dx. And in this case, dz dy is negative 3y minus 3 minus 1 times dy dx. And in this case, dy dx is 15 times 1 times x 1 minus 1, and I can write that as negative 3y squared times 15x. Okay. Oh, thank you. What I meant to do is this, and then one more. Sorry. Ooh, thanks. You guys don't get to do this on tests. So. No, tú tienes razón, es menos 4. Okay. In this class, many times we're going to have functions with multiple variables.
And you still have the X there. You just begin.
It's late, I guess. You guys want to start this up? Okay. Oh, sorry. Thank you. I'm glad you're. Okay. In this class, most of the time we're going to have functions with multiple variables. Right? And what we want to do most of the time is I want to see the rate of change in just one variable, how that affects my dependent variable. Right? When I do that, I'm making an assumption. I'm making the assumption that the change in the variable that I'm concerned about doesn't affect the other independent variables. Right? In other words, I'm going to take those as constants, right? And just treat them as constants. So if they're multiplied by one of the variable that I'm concerned about, I just bring it along. If not, right, the derivative is 0. Right? That's known as a partial derivative. So suppose I have a function y is a function of x1, x2, and so on to xn, a bunch of x's, right? But I want to isolate how just x1 affects y, holding all the other variables constant. Right? Now, what I do, right, is I take x1 plus a small change in x1, I didn't have to do that small, x2, x3 holding those constant, minus the original one where x1 doesn't change, x1, x2 to xn, all divided by the change in x1, right? And that gives me how y changes when x1 changes. Now, when I want to convert this into a derivative type function, I just take, I'm going to have to come down again. I just take the limit on x1 or on delta x1, the change in x1, as it goes to 0. Right? Not down. And once we do that, I get something that's very similar to a derivative, but conceptually different because I'm holding other variables constant. That is known as a partial derivative. So we take the limit as x1 goes to 0, right? And what I use are these things right here. They're called deltas. I don't know why they call them deltas, because I guess for most things, we use the Greek letter delta. This isn't a Greek letter, and it's not a Greek letter delta. For this class, I'm gonna do my best just to call them partials. So when I have this, I have the partial of y with respect to the partial of x1. Right? This is, I'm taking the derivative with respect to x1, holding all the other independent variables constant. Okay. So with partial derivatives, right, I have a multivariable function with respect to only one independent variable. Okay, so if I have y is equal to 3x plus 5z plus 2x times z, what would be the partial of y with respect to x? Okay. So what I want to do is first of all, I want to find all the variables or all my elements that have x. If this one does and this one does, this one doesn't have x. So what do I do with it? I treat it as a constant, and therefore the derivative is, I like that. How does it go? Perfect. 0. So I have 3x, and this one I'm just going to write 3 plus 2. Of course, x is here. Here, actually, let me do it. Sorry. 3 x times 1, x1 minus 1 plus 0 plus 2 times 1, x1 minus 1 times z is crunched up there. Sorry. So I have 3 x2 0 plus 2 x2 0 z, or I have 3 plus 2 z. That's the partial of x, and partial of y with respect to x. But we have another variable. What's the partial of y with respect to z? Well, derivative here, the big 0. This is z. Close enough. So I have 0 plus 5 times 1, z 1 minus 1 plus 2 x z, oops, 2 times 1, sorry, x to the z, 1 minus 1, or 0. I have 5 to 0 plus 2x z to 0, or 5 plus 2x. That's a partial. Okay. Now, this is going to be important for us, just the partials, when we do functions and we try to figure out the elasticity of certain variables in that function. And as I said before, for, let's say, demand elasticity, it tells us how elastic, right, a certain demand for a certain variable may be. But we can apply elasticity to anything because it's the percentage change in one variable divided by the percentage change in another variable, right? We're going to see we can calculate that mathematically when we have functions. Okay. So we have the partial derivatives, we can do differentials, right? A differential or a differential quotient, y and x can be written as an identity. So I have delta y is equal to delta y over delta x times x. Now, this is identity. I have delta x here and delta x there. Basically just one. We're just doing a sleight of hand and algebra, right? So when the change in x is infinitesimal, right, we take a limit when x goes to 0, the change in x goes to 0. The change in y will also be infinitesimal. For infinitesimal changes, I change the deltas, right, and write it as d, like I do with the derivatives. So I write it as dy dx. Therefore, the infinitesimal changes in the identity can be written as follows. Right? Dy is equal to dy dx dx, right? Which I can write as, or I can write it fx prime dx, right? Now, this is, for the most part, just an algebra trick, but it helps us conceptualize, right? We're going to totally differentiate. And when we totally differentiate, basically what we're doing is taking all the partials and adding them together with the ends, with the d, with the dz's and the dx's on the bottom. So I'm concerned with just dy, and then I do all the partials. Okay? So keep in mind that for infinitesimal changes, therefore a non-linear function, and substitution of larger changes for dx will result in small errors in derivation. As can be seen in the graph, right? F of x equals 2 plus x squared is the next slide. At x equals 1, the function gx 1 plus 2x is tangent, right, to f of x 2 plus x squared, which means the slopes are the same at that point, at point A, where x equals 1. Here the two functions have the same slope. At this point, f of x equals 3, g of x equals 3, and the derivatives are also equal to 2. As we move to the right, the change in x gets bigger. The difference between the two derivatives gets bigger, and I want to say, in fact, when x equals 2, right, f of x equals 6, g of x equals 5, and the derivatives are no longer equal, this gives us an error of 2. The farther away we get from x equals 1, the bigger the difference in derivations will be, and the closer we get, the more accurate g prime of x will be at determining the derivative. So that's basically the graph I was talking about right here. The tangent, but here that linear function, right, is far off the actual function. We need the actual derivative, the top one there. Okay. So the process of finding the differential, dy, is called differentiation. In order to avoid confusion with the differential d of y, one should use the differentiation of y with respect to x when I take the derivative dy dx, right? So here the differential, right, for dy, when I have the x's, is as follows. I have dy dx. So basically what I'm doing here is I'm just using my sum difference rule, right, with a bunch of power rules in there. But I want the differential, not just the derivative. That's a derivative. How do I get the differential? Real easy. It's just a sleight of hand. I just take that d of x and I move it over. Right? So I have dy equals 21x squared minus 10x plus 6 dx. That's the differential. That's probably something you never saw in your calculus class. But for our purposes, it's that simple. It can get a lot more complicated, but not for us. Okay. Another one, right? Y equals 4x minus 3 times 3x minus 8. So dy dx, I go ahead and write them through. I get 24x minus 41. And I could do this 100 different ways. I can do it with the product rule. I can do the math and then do it. Either way, you'll always get the same thing, right? And therefore, my differential is dy equals 24x minus 41 dx. Okay. Why did we do that? To get to total differential, right? For a function of two or more variables, the total differential measures the change in the dependent variable brought about by small changes in each independent variable. Remember, when we did partials, we're assuming the other variables are constant, right? So here, dz is going to be z of x, where z of x is the partial of z with respect to x, dx, plus z of y, where z of y is the partial of z with respect to y, dy, right? So what I do is I take the partials, right, add them together, and then make it a differential. Okay. So for instance, when I have that basket of goods that we're talking about, and I'm measuring utility, I'll call u as a function of utility, x1 to xn, right? Where x and five is good, I can write the total differential as follows, right? So I want to know how utility changes, or how to change in something. I can do the following. That's du equals the partial of u with respect to x1, dx1, partial of u with respect to x2, dx2, and so on. And of course, I can write those partials just to save notation. Du equals q1, dx1, u2, dx2, all the way to un dx. For u1 dxn is a change in u resulting from an infinitesimal change in x1, right? Economically, it's the extra utility received from increasing x1 by a small amount or the marginal utility of the first commodity, right? So basically, all of these gives me how utility changes when that x changes by a small amount. Questions? Right? Mathematically, we're just doing calculus. It's conceptually, it's a little different. Notationally, it's a little different, but it's really calculus. Okay. So I'm not going to go through the rules of differentials because they're pretty much the same rules as derivatives. All we got to do is apply the basic rules of the derivative and add the differential, the du's and the dv's. Questions? Okay. Do you guys want to go through the exercise? Or do I just look at the skin right now? I see the faces isn't over. Okay. So our total differential, right? The first I take the partial of z with respect to x, then I take the partial of z with respect to y, and I have my two partials. Then I could just put them in, right? The first one, the partial of z with respect to x, dx. Then plus, or the partial of z with respect to y, dy. And there we have it. That is our total differential for z given that function. One more time. I have z equals 7x squared times y cubed. I take the partial first with respect to x, then with respect to z. I put the the dx and the dy, add them together, and I have the total differential for z. By the way, if I'm going too fast, you can slow me down.
Wouldn't the in the first differentiation, wouldn't it be 14x? Because the y is not contemplated in that first part?
No, it's treated as a constant. So it would be, just like the 14 stays, the y stays, the y cube stays. Okay. The next thing I want to talk about is optimization. When we did calculus, hopefully we did some optimization, right? And in general, when we want to optimize, either take a maximum or a minimum of the function, what's the first thing we do? Okay. I think I understand. We take the derivative, right? And then once I have the derivative, what do I need to do with that derivative? And set it equal to 0. And that'll tell me if it's an optimum. It won't tell me if it's a maximum or a minimum. To do that, we need the second derivative. We'll talk about that a little later. Right. We might also have global or local. I don't know if it's the biggest or just a point where it tops and comes down, but there might be another point where the highest one is a global optimum. The other ones that top off or bottom off are called local optimum. Right? So this is just a bunch of notation. Local extrema will be extrema in the neighborhood around where the extrema is located. Right? That's all that means is you'll have this, and this are all maximums, right? They're all maximums. These two, right, are local maximums. This is a global maximum because it's greater than it. These are all minimum. These two are minimums, right? This is the local and this is the global, because it's the lowest point of the entire function. Entire domain. Now, perdona? Yeah, well, okay. I'm assuming that's our domain from that point to the other. Then we have situations where, right, I can take that derivative and make it equal to 0, and it's neither a maximum or minimum. But on 2 dimensions, a saddle point. Whether it's neither a maximum or minimum. And that's why we have to take the second derivative to know if it's a maximum or minimum. I take the second derivative, and if the second derivative is positive, what do we have? A minimum. Negative? Maximum. There was only 2 choices. If one was a minimum, the other had to be the maximum, right? I'm sorry? Oh, so when it's equal to 0, then we have this situation right here, where it's an inflection point. Okay, so we need higher order derivatives for now. Right? And higher order derivative is just a derivative of a derivative. I take that first derivative, I get whatever function's there, I take the derivative again. That's the second order derivative. I take it one more time, it's the third order derivative, and so on. But for maximum minimum, all I need is the first 2, right? So here we have a maximum, right? At point A, right? The function's increasing at a decreasing rate. At point B, we have a derivative of 0, and the second derivative, right, would be negative, right? So here, first derivative positive, second derivative negative. Here, first derivative 0, second derivative negative. Here, first derivative negative. Second derivative? Increasing negative. I'm sorry, decreasing negative, increasing negative. Okay. I'm sorry, you're both negative. Wait a minute. Yeah, that's right, it's negative, sorry. Decreasing. Okay. So, first derivative is positive, second derivative negative. First derivative 0, second derivative negative. First derivative negative, second derivative negative. Here we have a minimum. So here the first derivative is negative, 0, positive. What's the second derivative here?
0.
Oh, I'm sorry, here. Huh? It's decreasing, right, at a decreasing rate. Positive. But it's easy to get confused. It's decreasing, but at an increasing. Is it increasing faster as you move, or is it decreasing slower as you move? The first one, I'm sorry, the second one is 0, but the second derivative is positive, and again, over here it's positive. It's going, it's getting positive, but it's getting positive. It's going positive faster. So the second derivative is positive. I'm sorry? Okay, if that helps you remember, it's great. Me, it's not logical. I don't see the logic there. But if that helps you remember, that's great. I just try to remember, right? Is it getting higher faster, or is it getting higher slower? And of course, that didn't help me a while ago because I got that one wrong. So maybe the U is a better way to do it. Okay. Optimization of multivariable. Again, we're going to do the same thing, but now we have more than just 2 dimensions. This is basically when we apply our total differentiation. Suppose I have a function z that's a function of x and y. That can be a maximum or minimum, right? The first derivative needs to be equal to 0, right? That ensures that at a given point the function is neither rising or falling, so it's an optimum, right? The second order partials, right? I take partial with respect to zx, zy, right? They both should be positive, right? Excuse me. They both should be positive for a minimum and negative for a maximum. Okay. This ensures that the critical value of the function is moving upwards in relation to the principal axis in case the minimum and the downward relationship to the principal axis is a case of the maximum. And the final critique that we need is something known as the cross partials, right? That is zxx plus zyy, that's the second partials, has to be greater than the square of the cross partial. And the cross partial should be equal to one another by something called Young's number. But zyx, right? So I take the partial with respect to x, and then I take the partial with, once I do that, I take the partial with respect to z, square. As long as this partial times this partial is greater, right, we have an optimum. If it's not, what we have is known as a saddle point. So if it is, sorry, we have one of these 2 situations. Oh man, it looks so good here, look. Here we have a bowl, right? The bottom of the bowl. And here we have a maximum. If this third condition isn't realized, right? Like our inflection point, we have what's known as a saddle point. Oh, is this, oh, you guys don't have it. I have I have a graph that has a saddle point. It looks just like a saddle we put on one, right? And I can't draw in 3 dimensions, but it looks like this where this is this way and this is ahead. It's a saddle point. It's neither a maximum or a minimum at that point. It looks just like a saddle, right? One part goes like this, and the other part goes like this. Okay. Now, I'm going to give you something that you may not achieve. Hope, like I said, I assume that most of you have seen calculus at least a little bit. But this is something you may not have seen, and these are integrals. And basically, it's all the rules that we have, just backwards, except for when we get to logs and stuff. The first one is rule 1. Basically, the integral of a constant, right? The integral kx is going to be k times x, I'm sorry, k dx, k times x plus c, where c is a constant. What does that mean? It means an integral or an antiderivative is the opposite of a derivative. So if I have a function, y equals 5x, I know that the derivative, right, dy dx is just equal to 5, right? But once I have 5, what do I want to get back to this, what I do? Well, I take the integral. Now the integral, right, is going to be 5x plus c, which is a constant. I have no way of knowing if there was a constant here. There is a constant here, it's 0 in this case, but I have no way of knowing that. I just know that there's something there, or there should be something there. So it's 5x plus 0 in this case, or c. And that's rule 1. It's just the anti-derivative. And that's what an integral is. Rule 2, right? The integral of 1, simply written as dx, not 1 dx, is the integral 1 dx is x plus c. So instead of 5, right, I have 1x, 1, and I have x plus c, or 1x plus c, or just x plus c. It's basically rules 1 and 2 are basically the same rule. It's just for some reason students get confused when they see a 1 relative to other numbers. Rule 3, the integral of a power function, x of n, right, is given by the power rule. Yeah. So if I have y was equal to x to the 3, dy dx is equal to 3x squared, right? So I guess, okay, let me write the rule down over here instead of waiting for the board to come down or the screen to come down. That's the rule. You can't see here. So here, I want to get back to that, right? So the integral 3x squared dx is going to equal 1 over 3 plus okay. And in this case, oops, and sorry, n is 2 here. So here what I have is 1 over 3 times 3, x to the third, 3 over 3 is 3, so I get x to the third plus, plus c plus c. So x to the third plus c. Again, we have a constant at 0, but I have no way of knowing that it's 0 or some other constant. Okay. Oh, of course, in this rule, n can't equal -1. Why? Because then I have -1 minus 1. I'm dividing by 0. We know we can't divide by 0. Okay. This is one, it's just one of those rules that you have to remember. It's just the way it is. I mean, there's no rhyme or reason. It's just, that's the way natural laws work. It's just a rule in nature. So the natural log of x, if I take the integral of the natural log of x, I get 1 over x. Okay. So x to the -1 dx, therefore, will be the log of x plus c for any x that's positive. For an x that's negative, I have log of the absolute value of x plus c. And of course, x can't equal 0. And it has to be an absolute value. Why? Because it can't equal log. Questions? Okay, rule number 5. We need to learn the derivative of an exponential function. First, we get into natural log form. So if I have a, where k is a constant, x is a random variable, I take the natural log and I get k times x, the log of a, right? The derivative of this with respect to x is going to be dx dx kx times the log of a, or k times the log of a, because x goes away. If I take the natural exponent, right, I have, you guys can't see that, I'll write it here. E to the k times the log of a, and that's just going to equal a to the k. Right? I take the integral of that, log, you can't see that, maybe I can. So I have the integral of a to the kx dx, and that's going to equal a to the kx over k, the natural log of a plus a constant. Okay. The integral of a neutral exponent function, that's the integral of e x to the k, is just going to equal the exponent xk over k. When I do the e over k, I just take the k downstairs. In other words, I take the derivative of this, and it goes in the numerator. So if this was x squared up here, the down here would be, right, 2xk. Of course, plus. Okay. Rule number 7, the integral of a constant time function equals the constant times integral. So I have the integral of k f of x. I just take k to the outside of the integral, and then I can work with just the integral. Right? And rule 8, the integral, the sum difference of two or more functions equals the sum of their integrals. Now, this is the sum difference rule. And finally, for our purposes 9, the integral of a negative of the function equal to the negative of the integral. I can think of that negative function as just -1, right? Just a constant. I take the -1 outside, or I take the negative sign outside. It's the same thing. So rule 9 is similar to rule 7. Okay. First example, suppose I have the integral of 3, is what we did up there. I had 3x plus c. Am I going too fast? 2, suppose I have x squared, which is the integral of x squared. Well, I did it up there. I don't know if this was subconscious that I did them, the same ones that I had up here. I probably shouldn't have. So I get what? 1/3 and x to the third. Of course, over there I had 3/3, so it helped. And of course, plus c. I always have that c because the derivative of constant is 0. And I might have had a 0 when I took that derivative. I don't know. It might have been some other number. But anyway, the derivative is 0, so I don't know what that constant is. I have no way of ever knowing what that constant is. Okay. Okay, I'm going to do Young's theorem. And I'll let you guys just read on implicit functions. But Young's theorem says that if I have second order partial derivatives, right? F of ij, it's going to equal f of ji. In other words, it doesn't matter what order I do it in. I can take the derivative with respect to one variable and then the other, or I can do it the opposite. I can do I first and then j, or j and then I. They're always going to be equal. That's Young's theorem. I'll let you guys read implicit functions because for micro, we don't need it. Depending on who teaches macro, you may need it, but he could teach it in macro. And implicit function theorem, and hey, I'm letting you guys out right around. This is usually about the time. I know it's late. I know you're tired. I know you have to get home. You have to probably eat dinner, get ready for tomorrow and Monday in the morning. So I'll do my best to let you guys out here. Okay. Questions? Questions on the class in general? I apologize for those of you who had a hard time making it on Saturday. Basically, when I was given this class, which was about 2 weeks ago, I knew I would probably get the class. In fact, I knew it when they first told me I wasn't going to teach the class. Because they said they were going to get somebody else to teach the class. Okay, that's fine. But it's hard to find somebody to teach a class, and I knew there was nobody in the department from Friday that would want to teach a class. That means they have to get somebody from somebody else and probably get somebody to teach a class for basically what we paid to teach a class, of one class. And I knew they were going to have a hard time. So I expected it, but I wasn't sure. And it doesn't hurt too bad because I taught the class before as much as it does the undergraduate class that I had, because I didn't get prepared for that class. And that's when I teach in Spanish and my Spanish before, especially when I teach. So, okay. No questions?
Class is 7 to 9.
I'm sorry?
7 to 9. That's the time.
Officially it's 7 to 9:50. I'm going to try to get you guys out of here right around 9.
That's how it was going to be. Right.
Officially it's 6 to 9. Well, officially it's 4 up. And we have people that are traveling a long ways. I asked if we could do it at 6:30 and they gave me $30, so I'm not even gonna try. Okay. Okay. And basically, I apologize for those of you who can't make it on Saturday. Basically, no matter what I did, I was gonna have people that were gonna be upset with me. Couldn't make it. And I apologize. One Saturday, yes, one Saturday, no. So it's not every Saturday, it's just every other Saturday. So this Saturday, we're gonna meet, here at 11 o'clock. I know some of you guys want to be at 10, but I'm not the only person, especially on the weekends. So I split the difference. And I made it 11, so officially it's gonna be 11 to 1:50. We should be out of here by 1. You're not too hungry at 1. Exacto, exacto. Ese es el compromiso que.
Una semana, nos reunimos miércoles y sábado, y después la próxima semana.
So those of you can't make it either on Wednesday or Saturday, you're only missing half the class.